Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 9th, 2025, just yesterday. The striking result is a simple human-in-the-loop phase that teaches robots to recover and then correct during failures, which delivers robust long-horizon manipulation with roughly an order of magnitude less teleoperation data than prior work. The paper is titled RaC, Robot Learning for Long-Horizon Tasks by Scaling Recovery and Correction. And as we will see later, the implications for training data design are quite significant. In short, interventions that rewind to familiar states and then complete the subtask boost success and enable test time scaling. On X, researchers highlight 10 times data efficiency and praise systematic recovery and correction that lets policies reset and retry, leading to stronger performance. Engagement looks moderate, with roughly 100 likes. Alright, the previous segment framed why success-only imitation plateaus. Figure 1 shows the workflow that adds recovery and correction so the policy learns to retry and adapt. The top row depicts an autonomous rollout that drifts, followed by a human intervention, which rewinds and then corrects. The center schematic explains how trajectories include recoveries and corrections that are used to train the policy, which drives higher success with less data. The bottom row illustrates a rollout that succeeds after inserting recovery maneuvers. So the previous figure contrasted correction only with recover, then correct rollouts. Figure 2 shows the physical platform that makes those interventions practical, with 2 7-degree of freedom arms, soft grippers, and synchronized cameras. The overhead camera and the 2 wrist cameras provide multi-view images, which feed the policy and the heat map guidance tool. The VR joysticks enable quick human recovery moves, so operators can rewind to familiar states and then complete the subtask. Alright. The previous figure focused on hardware and sensing for bimanual control. This table presents algorithm 1, which formalizes the recovery then correction data collection, so interventions follow 2 rules. The loop collects expert demos, then runs rounds where a human intervenes only when failure looms, pairs a recovery with a correction, and ends the episode after the intervention. Full robot successes go into the dataset without charging human budget, which preserves efficiency and keeps training distributions clean. Well, the previous table laid out the intervention loop. Figure 8 shows how performance scales with human-collected frames across 3 real-world tasks, and it also compares against HG Dagger and full demonstration cloning on shirt hanging. The top row tracks task progress scores, which rise steadily with more data. The bottom row reports success rate, and the blue stars surge after roughly 6 to 9 rounds, indicating strong data efficiency. The right panels show clear gaps over baselines for the same budget, so recovery then correction delivers steeper scaling. So the previous figure showed steeper scaling for recovery then correction. Table 1 compares shirt hanging results head to head, and it highlights data efficiency and accuracy together. The RaC policy, a flow matching transformer with about 368 million parameters, reaches 78.3% success using roughly 5 hours of mixed expert, recovery, and correction data. ALOHA Unleashed reports 75% with about 89 hours, while CGR-3 lands near 63.6% with 116 hours. The comparison matters because it isolates the benefit of intervention composition rather than model size alone. Wrapping up, 2 takeaways stand out. Pairing recovery with correction reshapes the dataset so policies learn to reset and retry, which cuts human data needs by roughly 10 times, and success scales with the number of recoveries at deployment, showing robust long-horizon behavior. The broader implication is that data composition, not new objectives, drives big gains. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.